My name is Samir Khan and I'm one of a team of application engineers here at MapleSoft. My role and the role of other application engineers here at MapleSoft is to speak to our customers and to help them use and understand our tools, technology and services. This webinar is about signal processing in Maple. Now, without further ado, what I'd like to do is actually show you two signal processing applications in Maple. So let me just switch into Maple and demonstrate a couple of applications. And the reason I'm doing this straight away is because signal processing and Maple are two very broad terms, and they mean many different things to many different people. Maple is a flexible environment and the look and feel of it can change depending on who authors the document. This is one typical application for Maple. It's an application in which we're investigating coded excitation signal analysis. I'm not going to spend too much time talking about the actual concepts embodied in this document, but I just want to look at some of the elements you see on screen. So at the top we have a header graphic and a title which describes the problem domain. We have a diagram, and then we have text and math. The math is in natural math notation. So we have proper integrals, proper Greek letters. We view the results of our application in the form of plots, equations, numbers, or a combination of those elements. And we also have various interactive elements inside this document as well. So if I scroll further down, this is an animation in which I'm looking at the autocorrelation of two signals, and if I move this bar, I can change the offset between one of the two signals and see how they interact. So this is just one particular look and feel for a Maple document. Now, if I wanted to, I could also produce an application like this and deploy it free of charge in the Maple player. It generates spectrograms from an audio file. All I have to do is click on a button and load a wave file. I can apply a window and plot a spectrogram. If I wait a few seconds, I'll see the spectrogram here. So this is a spectrogram of a DTMF tone, and you can clearly see the individual tones in the spectrogram together with the constituent frequencies of each tone. If I wanted to, I could also apply a filter as well. So let's pick a high-pass filter. And if I scroll down to the power spectrum, I need to specify a cutoff frequency for my high-pass filter, and I do that simply by clicking at the appropriate point on the power spectrum. I can change the order of the filter, replot the spectrogram, and again, if I wait a few seconds, I can see the updated results. Now, if I wanted to, I could also change the color scheme as well. As I said, this application is suitable for free of charge deployment via a technology called the Maple Player. So I just wanted to show you these two applications right at the very start, just to place the rest of this webinar into context. So let's just switch back into the slides. Now, I'm actually part of a consultancy group, and we solve problems and model engineering systems for our customers. And this is typically the type of work that we get involved in. Recently, we've built a systems level model of a piezoelectric stepper motor using high level electrical and mechanical components. In our tool chain, you can then simulate this high level model to get the time-based results. Now, piezoelectric motors are typically associated with frequencies in the ultrasonic range, maybe 100 to 200 kilohertz. If we want to, in our tool chain, we can also plot the power spectrum and the spectrogram. And although it may be difficult to see, I think we can see that we have frequencies of around 150 kHz in both the power spectrum and the spectrogram. And this is the power of our toolchain. You can model your engineering system, and then you can perform some kind of signal processing analysis, some kind of frequency domain analysis. So some of you may not be familiar with the tools that MapleSoft offer. We have two primary products. Maple is our tool for math and modelling. It's essentially our flagship product, our brand ambassador, and it has a heritage of well over 20-25 years worth of continual development. It's essentially a tool for doing math on a computer, and it has both a symbolic and a numeric math engine, and there are visualization tools as well. Around Maple, we built an ecosystem of supporting technologies for global optimization, deploying Maple applications to the web, and grid computing and multi-core math as well. Several years ago, we released another tool called MapleSim. It's our multi-domain physical modeling tool. With MapleSim, you model with high-level physical components, so things like resistors, capacitors, sliding masses, multi-body components, and so on. So MapleSim actually runs on top of Maple. This means that MapleSim uses the symbolic and numeric math technology that we've refined over the course of 20-25 years to extract the system equations from a model, optimize them, and solve them numerically. Moreover, we've added tools for controls design, time modeling, driveline modeling, and connectivity into real-time tool chains like Symlink, LabVIEW, and DSpace. And by and large, we're going to concentrate on Maple during the course of this webinar. Now, as a part of this webinar, we prepared a signal processing technical resource pack. It's a collection of Maple applications that explore various concepts in signal processing. If you'd like an archive of these Maple worksheets, then please contact us at support@maplesoft.com. So there are applications for signal denoising with FFTs and wavelets, frequency domain systems identification, spectrogram analysis of various audio files. In fact, there's an interesting spectrogram of a car engine noise, and you can clearly identify the shift points of the gearing system by the spectrogram. There's an application which looks how you can reduce the complexity of brain MRI images to make them more compressible. There's a theoretical and practical introduction into wavelets technology. There's an interesting application in which we examine the periodicity of sunspot data. I might demonstrate that later. There's an application for tune mask damper design. Also, we're finding that signal processing concepts are finding applications beyond their traditional engineering domain. So, although not many people know this, you can actually price financial options using signal processing concepts like FFTs. There's an application submitted by one of our users which looks how you can analyze blood pressure and pulse analysis data. And there's an application for coded signal excitation analysis. And as I said, if you'd like a copy of this, please contact us at support@maplesoft.com. So in terms of signal processing functionality, we have tools for signal generation. You can visualize results in the form of a variety of plots, including power spectrums, signal plots, spectrograms, and a whole range of other visualization tools as well. There are tools for sample conversions. There are tools for FFTs and various classes of wavelets, convolution and correlation, windowing. You can design FIR and IIR filters, and you can resample signals as well. Now, this is in addition to the other Maple functionality for symbolic and numeric math, code generation, programming, and so on. In terms of the application scope, you can design filters, you can apply windows, you can denoise and smooth signals. There are tools for frequency domain analysis and feature extraction, and you can analyze real-world data as well, so audio analysis, speech analysis and segmentation, vibration analysis, systems identification, and so on. Now, signal processing is a broad term and it has many different nuances. For example, signal processing means different things to data scientists, electrical engineers, mechanical engineers, or biomedical engineers. For example, a biomedical engineer may want to smooth blood pressure and pulse data with wavelet technology. An automotive engineer may want to analyse a spectrogram of a real engine sound to identify characteristic frequencies, or an electrical engineer may want to model ultrasound transmission through bandgap mediums. So in the space of a short webinar, it's difficult to cover all of the bases. So in this webinar, rather than focus on the minutiae of signal processing in one discipline, I'd like to provide a broader overview of why you'd want to use Maple for implementing and exploring these concepts. So we'll talk as much about Maple in general as we do about signal processing. Now, Maple's been traditionally known as a computer algebra tool, and that's a fundamental, critically important part of its heritage. Many engineers have used Maple at university in their calculus courses to solve differentials and integrals. There's also a significant amount of numeric computation features in Maple as well, one part of which is signal processing. So why would you want to use Maple instead of other tools, other more traditional tools for signal processing? And by traditional tools, I mean command line oriented tools like MATLAB, as well as high-level programming languages like Python. I've also known engineers use Excel for signal processing as well, and frankly that's a really bad choice for signal processing, let alone any other engineering task, but that's the topic of a whole other webinar. So many of these traditional signal processing tools are essentially coding environments. You write flat 1D code. The commands, the code, are essentially programs, and that program may look something like this. If you want to document the code, you have to write inline code comments. These code comments have no richness, there's no formatting to them, and you can't include diagrams or pictures inside the actual program itself. Any plots are given in a separate window. In short, there's little feedback between the context of the application, the commands, and the results. But as an engineer, I feel that a continuous, smooth flow of feedback is critical to productivity, especially if you're developing new algorithms or just exploring the solution space. There's also questions about the maintainability of programs written in an environment like this. It's more difficult to share these programs in a team because it's certainly more difficult to get a sense of the conceptual flow of a program. A Maple document, however, is a much richer environment, and I think you saw that in one of the applications I demonstrated at the very beginning of this webinar. You can include equations in natural math notation, explanatory, fully formatted text, just like a word processing environment. You can copy and paste in pictures and other elements from other environments. This essentially means that you capture the assumptions, background information, as well as the calculations in a single integrated environment. I'd also like to highlight the quality of Maple's visualizations. You can produce some very, very visually impactful plots and charts, and you can finesse the look and feel of those plots right down to the precise color grading of the color range in a spectrogram. The plots and visualizations are inline in the worksheet. That gives you a closer connection between the algorithm and code and its visual representation, the results. Maple also talks to other tools and data sources. Now, at its simplest level, you can simply import data from an Excel spreadsheet or a CSV file, but at a far deeper level, you can communicate with MATLAB. So, for example, if you have MATLAB and Maple on your computer, you can exchange information, equation, and data interactively between the two applications. Maple also talks to CAD packages like NX, Autodesk, or SolidWorks. This means you can develop a parameterized CAD model, extract its design parameters and constraints into Maple, perform some kind of design optimization, then push those optimized parameters back into the CAD model. And Maple also talks to network data sources. So I'd actually like to demonstrate this in a Maple worksheet. So let me just switch into Maple again. So this is one of the applications in the Technical Evaluation Resource Pack. Here we're looking at the periodicity of sunspots. To do that, we need a source of sunspot data, and that's actually available online at this website. In this command, we're connecting to this website and downloading a data file of sunspot data. This data file is updated continuously, so if I run the application next week, I may get a different set of data. So the data is actually represented in a shorthand notation like this, but if I actually want to see the data, I can extract the individual elements using Maple's programming operators, or if I double click on this representation, I get the matrix browser up on screen. So here I've downloaded 2 columns of data from this website. The first column is years, and the second column is the sunspot data right up to the present day. Using Maple's functionality, I can plot this data, I can calculate the periodicity via a fast Fourier transform. So here, in this power spectrum, the peak frequency is at about 0.09 years to the -1. So that's about a period of 11.1 years, I think. If I wanted to, I could calculate the autocorrelation of the sunspot data as well. And again, I can identify the peak frequency of just over 11 years by the autocorrelation as well. Now, once you've developed your Maple application, you can deploy it free of charge via the Maple Player. And this is essentially a free runtime version of Maple. It's a free download from maplesoft.com. So the concept is that you can use your main license of Maple to develop your applications using all of Maple's signal processing functionality. You can use a variety of graphical elements, including sliders, dials, gauges, and push buttons to introduce a degree of interactivity into the document, and then you can deploy that document free of charge via the Maple Player. Now, the spectrogram generator I showed you earlier is demonstrated in the context of the Maple Player, and as I said, it's a free download from maplesoft.com. So that was essentially why you'd want to use Maple for signal processing. It's a documentation environment. You can visualize your results, and you also have connectivity and deployment options as well. Now, all of that is in context to the other Maple tools for optimization, matrix computation, solving differential equations, finance, control systems analysis, systems modeling. We've also introduced technology for automatically parallelized computation and code generation as well. So this is a screen grab of some Maple equations. It's a differential equation written in dot notation. Using Maple's context-sensitive menus, I can solve the equation symbolically and then convert the result to as the C language description. Now, we've had signal processing functionality and tools for Maple for some time, But that code was getting rather dated and it didn't make use of modern CPU specific optimizations. So recently we've introduced a new set of signal processing tools based upon optimized math technology. The technology is much more memory efficient and it's much faster as well. And this is a benchmark. So let's say that we're calculating the FFT of 2 to the 26 data points. I think that's around 67 million data points. Maple's older FFT function would take around 13-14 seconds to calculate the FFT of that data set. Using Maple's newer signal processing tools, that drops down to a fraction of the time, about 3 or 4 seconds. And we're continuously making performance gains like that throughout the Maple system. They may not be as significant as this, but even a performance gain of 5%, 10%, when compounded over repeated computations, makes a real tangible difference to the user experience. Now, as I said, I'm part of an applications team that works with you to solve problems, and the group is headed up by Aram Vahid. He's a graduate of the University of Waterloo, and we have other highly skilled engineers who work in the team as well. We essentially work with our customers to solve their engineering problems. Now, what I'd like to do is dive into Maple and actually demonstrate a few simple concepts from scratch. So first of all, we're going to filter an audio file using our signal processing functionality. And I'm doing this from memory, so forgive me if I make a few typos. Now, this is what Maple looks like. I've already shown you a Maple document, so you're already familiar with the look and feel of a Maple document. Now, to import an audio file into Maple, I can use the import data assistant. And let's pick up this file. It's a DTMF tone. Let's assign it to a variable named data. Once I've done that and clicked on OK, Maple automatically inserts the appropriate command into my worksheet. Now that audio file has certain attributes: a sampling rate, a bit rate, and a number of audio channels. And I can extract that information by the attributes command. So we have a sampling rate of 8 kilohertz, and there's a single channel of data. I'm going to extract the sampling rate and assign it to a variable SR. And I'll do that like that. So let's load up our suite of tools for signal processing. Now, if I type this command, it loads up the suite of tools for signal processing, and here you can see some of the commands in the signal processing package. In the context of this demonstration, I don't need to see all of those commands echoed back at me, so I can simply bookend this with a colon and hit enter again. So let's just say that we want to plot the spectrogram of that data file. I can simply use the spectrogram function and give it my audio file. If I hit enter, it gives me my spectrogram. And here you can clearly see the individual tones together with the characteristic frequencies in each tone. So let's see if we can apply some kind of filter to this audio file. Let's generate a Butterworth filter. First of all, we need to generate the filter taps. Let's have a 9th order filter. We need to specify a normalized critical cutoff frequency of, let's say, 0.3. That's normalized with respect to the Nyquist sampling frequency and the sampling rate. And let's have a high-pass filter. If I hit enter now, Maple generates the filter tabs for me. So let's apply those filter tabs to our audio file. By the way, Maple has command completion, so if I just type in the first few letters of a command and I hit the escape key on my keyboard, the command completion menu pops up on screen. I can simply pick the command I'd like. So let's apply our filter to our audio file. And let's plot the spectrogram and perhaps the power spectrum of the filtered audio. And there we go. This is the effect of our high pass filter with these characteristics on our audio file. So you can see that this is clearly different from the pre-filtered audio file. Now if you wanted to, you could write out the updated filtered data into an audio file. What you can also do is fine-tune the appearance or the characteristics of the spectrogram as well. So for example, you can change the color scheme. Now I'm just typing in the commands to change the color scheme of this audio file. And let me specify a series of colors. If I hit enter again, you can see that the look and feel of the spectrogram has changed. Let's say that I wanted to highlight the most significant 10% of the frequencies in the spectrogram as well, the strongest 10%. I can do that by introducing a series of marker points. So let's say that I want the first 90% to be coloured from black to white, but the strongest 10% to be coloured from white to steel blue. I can easily do that. And here we go. You can see that the strongest 10% of our filter data is now coloured from between these two colours, white to steel blue. Now that was a demonstration of our numeric signal processing commands. A significant part of Maple is its symbolic math functionality as well. And this is just a simple demonstration of that. In this integral, I'm finding the convolution of a cosine under a hand function, a hand window with a cosine under a wider hand window. Here, I've entered the equation in proper mathematical notation. I've done this earlier because I'm sure you didn't want me to see me fumble and enter this equation in front of you. If I wanted to, if it made sense, I could actually change the structure of this equation, add in more terms. But if I hit enter now, Maple solves this integral symbolically and gives me a very, very large answer. This isn't something that you could have derived by hand. Now there's a variety of Maple tools to manipulate this equation. For example, I can simplify this equation with respect to its size. Or I can convert the result to different language descriptions as well. So let's just say I wanted to implement the results of this large symbolic expression into a coding environment, let's say Visual Studio, and I needed to convert this to C syntax. I can do this with our code generation suite of tools. Code generation allows me to convert this expression to a variety of different syntaxes, including C, C#, Fortran, Java, MATLAB, Perl, and Python. But let's pick C. And let's optimize the form of the symbolic result. And here's the optimized expression in C syntax. The optimize command essentially identifies repeated sub-expressions and factors them out. Those repeated expressions are then evaluated only once, but the result used many times. And I can just copy and paste this into a Visual Studio development environment, for example. So that was everything I wanted to show you today. It was a high-level tour of Maple's signal processing tools. As I mentioned earlier, we have a technical evaluation pack. If you'd like a copy of that evaluation pack, please contact support@maplesoft.com. If you have any application-specific questions, then please contact the applications team, of which I'm a member, at applicationsengineering@maplesoft.com.